Hi everybody, and welcome to the video for lesson 9.1, which is all about finding the area between two curves. Now we have two learning targets for today. The first learning target is I can calculate areas in a plane using an integral with respect to x. And the second learning target is I can calculate areas in a plane using an integral with respect to y. So we're going to be finding areas today, and sometimes we're going to do the problems in terms of x, meaning that x is going to be our variable, and sometimes we're going to do the problems in terms of y, meaning that there's going to be y's in our equations. Y is going to be our variable. Before we do any of that, I want to start with a quick review of what you guys already know. So what we learned earlier this year is that integrals are just areas. The first time we ever talked about integrals, we said that when you compute an integral, you're finding the area between the curve that you graph and the x-axis over a given interval. So on a graph like this would be the curve that you graphed. And when you find the integral, you're finding the area between the curve and the x-axis, which gives us these green areas, which we counted as positives, and these orange areas, which always counted as negatives. But again, your area was always trapped between the graph that you graphed and the x-axis. Now, what we're changing today is that we're going to be finding the areas between two curves. So that's the big new idea, is that instead of being the area between a curve and the x-axis, it's going to be the area between a curve and another curve. An example of a picture would be like these two pictures. For example, in this first picture, you can see that I want to find the area between the graph of y equals f of x, which is this curve, and the graph of g of x, which is this curve right here. I'm not stopping at the x-axis anymore. I'm going between those two different graphs. Another example of what this might look like is the second picture here, where I've got a curve that looks like this. And you'll notice that in the equation here, the x is by itself and y is the variable. We say that this curve is in terms of y. And I've got a curve that goes like this. And you'll notice that I'm finding the areas between those two curves. Now, this is where we have two different techniques for solving the problem, depending on whether the curve has one curve that's on the top and one that's on the bottom, like the first picture, where we've got a curve that is the top, and we've got a curve that is the bottom. Or depending on whether the area we want to find is trapped between two curves where one of the curves is on the right-hand side and one of the curves is on the left-hand side. Whether you have a top and a bottom or a right and a left, it changes how you would set up the problem. So let me give you an example. The area between two curves that are in terms of x, which was our first learning target here. So the first thing we're going to talk about is curves that are in terms of x on the interval from a to b. Now in this picture, a would be the beginning x value where those two curves intersected, and b would be the ending x value where those two curves intersected. You can find that area by doing an integral, just like we've always done, from a to b. But inside the integral, because you want to be between those two curves, what you put inside that integral is going to be f of x, which was the top curve here, minus the bottom curve here, which in this case is g of x. And again, because this is top minus bottom and we're going between two x values, we say dx here. Everything is in terms of x. Now, what you're often going to hear me say in the instructions is that this is a situation where to find the area, we are doing top minus bottom. And you're going to make that decision just kind of based on the picture, what makes the most sense. Is there a top and a bottom versus is there a right and a left in the picture? Now let's say that there is a right and a left curve in the picture. So instead of having a top and a bottom, you have a right and a left curve. We can actually find these areas in terms of y, which was the second learning target here. Now you'll notice that we do this on the interval from C to D. So in the first problem, we said we used the x values where the functions intersected. In this problem, because we're going in terms of y, we're going to use the y values where those functions intersected. So not the x values anymore, the y values, so from C to D. In the integral we set up, we're going to still set up an integral, and the lower number is still going to be C and the higher number is going to be D, but you'll notice that those are y values now. Again, not x values, but y values. Inside of there, we're going to put the right function minus the left function. Right minus left. I should be writing the actual names of the functions, shouldn't I? So this is going to be the right function minus the left function, which in this problem, they actually have names. And in this problem, the names are f of y is the right function and g of y is the left function. And then we're going to put a dy at the end because in this problem, everything's going to be in terms of y. Now, as we do examples, what you're going to notice is that in a problem like this, there are not going to be x's inside of your integral anymore. There are going to be y's inside of your integral. And again, the bounds are y values, and there's a dy at the end. So this is sort of all stuff that's in terms of y. Let's take a look at a few examples. So we're going to do some problems that involve using your calculator. This would be a great time to have your calculator out to help you. And we're going to go through a few examples together. The first example we're going to do here is actually a no calculator example. And this is a very typical type of problem that you might be given. It says, let's let R be a region in the first quadrant. So we're going to be in the first quadrant of the graph, enclosed by the graphs of f of x, which in this case I'm going to make blue, and g of x equals x squared. You want to find the area of that region. So step number one here is going to be to draw a graph. Now, again, we want to be in the first quadrant. So I'm only going to draw the first quadrant of my graph here. The graph of f of x, I'm going to make blue. So f of x is 3x, which means it starts at 0, 0, and then it goes up 3 over 1, up 3 over 1, and then up 3 over 1. So the graph of f of x looks like this. Now the graph of g of x, oh, and I should label this. I always like to label so I don't forget which one's which. In this case, I'm using colors, but a lot of times, like if you just have a pencil, it's good to label which one's which. If g of x, I'm going to make purple. So g of x is x squared, which has 0, 0, 1, 1, 2, 4, 3, 9, and it's going to be a curve. So it curves like this. Obviously, if I were to graph the whole parabola, there would be a whole nother side to the curve over here. But since I only care about the first quadrant, I'm only looking for the area in the middle between those two graphs because it says enclosed by those graphs. Now in this picture, if I look at the setup here and I ask myself, is there a top and a bottom or a right and a left? You could actually think of this picture either way. So there is a top, which would be my f of x function here, and a bottom, which would be my g of x function here. And the reason I can see that is that the purple is always below the blue. We're going to find the area of this region of the graph. Now in this problem, I'm going to do everything in terms of x because even though there is a top and a bottom, or you could say the purple is always to the right of the blue, there is a right and a left. In this case, everything has x's. So because both of these equations have x's in them, I'm going to do everything with respect to x. I like to say WRTX, with respect to x. That means that when I'm filling in my numbers, I'm going to use x values. My equations should have x's in them, and I'm going to set everything up that way. So to find this area, I'm going to do the integral from the beginning where those graphs meet which would be at 0, until the end where those graphs meet. And those are x values because I'm doing everything with respect to x. Now, inside of my integral, I'm going to put top minus bottom. That's the rule when you're doing things with x, is you're going to do top minus bottom. So in this case, the top function is 3x. And the bottom function, so minus, the bottom function is x squared. And I guess I can probably move this a little closer, right? Okay. So now in order to find the area, I just need to evaluate this integral. Since this is not a calculator question, all of the calculator questions will actually say this is a calculator question at the beginning. So since I want to find this area, I'm going to go ahead and just do the antiderivative. So the antiderivative of 3x would be x squared and then divide by the new power, so 3 over 2, minus the antiderivative of x squared would be x cubed and then divide by the new power, so 1/3, plus c, and I'm going to evaluate that between 0 and 3. If I plug in the number 3, I get 3 over 2 times 9, minus 3 cubed is 27, times 1/3 is just 9, plus c, minus if I plug in 0, I just get c. The c's cancel, so I end up with 27 over 2 minus 9. Now, as a note, 9 is really 18 over 2. So 27 over 2 minus 18 over 2 would just be 9 over 2. And that would be my final answer. The size of that area is just 9 over 2. Let's go ahead and look at another example. Now, this is actually going to be a calculator question. It says here, let's let R be the region of the graph enclosed by sine of x and cosine of x, as shown in the figure. R is going to be the region in the first quadrant. Step number 1 is figure out which one of these graphs is which. Now, because I've done graphing before, I know that sine of x, I wanted to use a highlighter here. I know that sine of x is going to be the one that starts high. That starts at 0, 0. I'm getting all disoriented here. Okay, that starts at 0, 0. So this is sine of x, and I'm going to go ahead and label that so that I can keep track. So this is y equals sine of x. And I know that cosine of x is going to be the one that starts at 1, so starts right here, and that's going to be cosine. Now that's important to distinguish because it's important to know which graph is which. Let's say that this wasn't a calculator question. You would need to be able to figure that out by knowing the basic shapes of the graph. Next, we need to find where they meet. In order to find the area between these two curves, we need to know where these curves meet so we know where to stop our area. I'm going to do that on my calculator. So on my calculator, I'm going to graph these two equations. I'm going to find the intersection point. And what I end up finding out is that the intersection point is 0.785,398, comma, 0.707106. Now you might be wondering, why are you writing so many decimals if you know that you can always stop after 3 decimals in calculus? And the answer is we want our final answer to have 3 decimals, but we want our work in the middle to have as many numbers as possible so that we don't lose out on the accuracy of our measurement. Now in this picture, I'm going to ask myself, do I have a top and a bottom, or do I have a right and a left? And I think it's pretty clear that there's a top and a bottom here. The purple is the top and the blue is the bottom. So because there's a top and there's a bottom, I'm going to do everything in this problem with respect to x. Whenever there's a top and a bottom, we do everything with respect to x. So I'm going to set up my integral. My integral is going to go from 0, which is where this graph starts, to 0.785398. And inside of that integral, I'm going to do top, which in this problem happens to be cosine of x, minus bottom, which in this problem happens to be sine of x. Now on your calculator, because this is a calculator question, you can actually type this in. So just like you can do derivatives on your calculator, one of the new things we're going to be using our calculator for is to do an integral. In order to find an integral, you just go to Math, option 9. It's very similar to how you got to derivatives, which was math option 8. To get an integral, you go to math option 9. You just type in all of this stuff. Please make sure that you're really careful. Make sure you don't miss any numbers or any decimals. And when you type all of that in, you should get 0.414 as your final area here. So this area between those two curves has an area of 0.414. Now let's talk about number 3. Again, this is a calculator question. Again, I'm going to graph it on my calculator in order to figure out not only which equation is which, but also where they meet. So my first equation here is y equals sine of 2x. Now I know that because of how I graphed this on my calculator, this is my sine equation. So that's going to be my f of x equation. And again, I want to graph and I want to figure out which equation's which. So the other equation here is x cubed minus 2x, which is this guy. And I'm going to find my intersection point, and you have the tools on your calculator to do that. I know that this intersection point right here is going to be the point 1.464342, comma 0.211302888. Now again, I'm writing a lot of decimals here. I want my accuracy of my final answer to be up to 3 decimal places, but in order to make sure that that's accurate, I'm going to use as many numbers as I can until I get to the final answer. Now I'm going to ask myself, is there a top and a bottom, or is there a right and a left? And I think it's pretty clear in this question that this guy is the top function and this guy is the bottom function. And anytime you have a top and a bottom, you're going to do everything with respect to x. So I'm going to set up my integral. The integral is going to go from my beginning x value, which is 0, to my ending x value, which is right here, 1.464342. And I'm going to do my top function, which in this case was the blue function, so sine of 2x, minus my bottom function, which in this case was x cubed minus 2x. Now I'm making sure to put that equation in a parentheses here because I want to make sure that I'm subtracting both parts of that equation. If I don't use a parentheses, then I'm really just subtracting the x cubed. Once I do that, I'm going to again go to math option 9. I'm going to type in this integral. And once I do that, I'm going to get that my final answer here is 1.983. So the size of this area right here is 1.983 units squared. Okay, now we've done a couple examples that all ended up being in terms of x. Let's look at a few examples where you would do the problems in terms of y and how you would handle that. This first example is going to be a no calculator example. So step number 1 is going to be to figure out which of these equations represents which part of the graph. Now, y equals x minus 1 is the equation of a straight line. So that's going to be this equation on the graph. If I look at the graph, I know that that's the right one because it's a straight line. So this would be y equals x minus 1. And the other equation, which is x equals 1/2 y squared minus 3, since there's a squared, it's going to be a parabola. Since it's a y squared, it's just going to be a sideways parabola. So it would be this guy. Now, based on this picture, I think it's pretty clear that there isn't one set top equation and one set bottom equation. It's actually going to be one equation's always on the right and one equation's always on the left. In this case, the blue equation is always to the right of the purple equation. Now, that means that I'm going to do everything in this problem with respect to y. And if I'm going to do everything in this problem with respect to y, that means I'm going to use y values. That means my equations should have x by itself and y in the middle, and we'll talk all about that as we work through. So first thing is we're going to use the y values here. So I'm going to use the lowest this goes, which is -2, and then the highest the intersection point goes, which is +4. So I'm using y values here. It's a little different than what I did before where I used x values. Instead of doing top minus bottom, I'm going to do right minus left. Now the right equation here is y equals x minus 1, but I again need everything with respect to y. So the first thing I'm going to do before I actually fill in this equation is I'm going to solve to get x by itself. Normally, we always are used to getting y by itself, but in this case, we want x by itself because we want everything to have y's in the equation. So to get x by itself, I'm just going to add 1 on both sides, which means I have y plus 1 equals x. So my first equation here, my right equation, is going to be y plus 1 minus my left equation. Now my left equation here already has x by itself, so I'm just going to go ahead and fill that in. 1/2 y squared minus 3. And then I'm going to put dy at the end. And again, it's because I'm doing right minus left. I'm doing everything in terms of y. I'm using y values for my bounds. Everything is a y variable here. All the x's change to y's. Now, in order to actually solve this, I'm going to need to do the antiderivative. So one of the things I like to do right away is distribute this minus. So this is going to be a negative and this is going to be a positive. That makes it a little bit easier for me because I don't make as many sign errors when I'm doing my antiderivative then. The antiderivative of y would be 1/2 y squared. The antiderivative of 1 would be plus y. Then I would have y to the third power, and I would need to divide by that 3. So instead of 1/2, I'd have 1/6 plus 3y plus c, and I go from -2 to 4. If I plug those numbers in, 4 squared is 16, divided by 2 is 8, plus 4. 4 cubed is 64, divided by 6. So 64 divided by 6, I believe, simplifies to 32/3. Plus 4 times 3 would be 12, plus c. Minus, if I plug in -2, I get -2 squared, which is 4, divided by 2, which is 2. Minus y is 2. -2 cubed is 8 is -8 times -1/6 is +8/6 minus 6 plus c. These c's cancel. I'm going to go ahead and finish up my work on the side over here. So 8 plus 4 is 12 plus another 12 is 24 minus 32/3. That's the first parentheses. 2 minus 2 is 0. And so I just have -6, but I have minus minus 8/6, there we go, minus 6. When I distribute that minus, I get a negative and a plus. And so 24 plus 6 is 30. 32/3 is really 64/6. So -64/6 minus 8/6 is minus 72/6, which is really 12. So 30 minus 12, which is 18. And that's how I'd find the area of this shape right here. Now, that was probably what I would think is probably the hardest one because there's so much algebra, there's so much arithmetic at the end there. Hopefully the setup makes sense to you, that you're doing everything with respect to y, because instead of a top and a bottom, you have a right and a left now. Now, the next few problems, hopefully the last few steps won't be as difficult because we are going to get to use a calculator. It's just a matter of getting it set up the right way. So for number 5, it says a calculator is allowed, and we're trying to find the area between the x-axis and the graphs of y equals the natural log of x and y equals 4 minus x. So the first thing I'm going to do is graph that on my calculator. Now again, I want to be in the first quadrant. So on the side over here, I'm going to sketch a little graph of what I'm seeing on my screen. In the first quadrant, here's what this ends up looking like. We have the natural log of x coming in like this. And we have y equals 4 minus x coming in like this. Now, since I want the area that's in the first quadrant, that means that I want this shaded area right here. So if I'm thinking about this area right here and I'm asking myself, is there a clear top and a bottom versus a right and a left? One thing that I want you to notice is if you think that the purple is always the top and the blue is always the bottom, you have to be a little bit careful there. If I, for example, look at this slice of the area right here, the top is the purple and the x-axis is the bottom. But if I look at this slice, the top is the purple and the blue is the bottom. So the bottom function changes. When that happens, it makes more sense to go from right to left. If you look at every single slice, if you draw them horizontally, the blue is always the right and the purple is always the left. So it actually makes more sense to do this in terms of y. Now, again, just like in the other problems we did where we used our calculator, we do need to find the intersection point here, which would be 2.926271, comma 1.073728.9. And I'm writing down so many numbers here. And the reason is just because I don't want to simplify it till I get to my final answer. Now, because there's a right and a left instead of a top and a bottom, I'm going to do everything in this problem with respect to y. So when I start setting up my integral, I know I'm going to use y values for my bounds. My lower bound here is 0, and my upper bound here is going to be this number here. So 1.073728.9. Now I'm going to do my right equation minus my left equation, but I need to be a little careful here. Remember, everything should be in terms of y. My right equation here is not in terms of y yet. It's actually in terms of x because y is not by, so x is not by itself. So what I'm going to do to get x by itself and have y in the equation is I'm going to add x to both sides, and I'm going to subtract y at the same time. Now, when I do that, I get x by itself equals 4 minus y. So my first equation in my integral here is going to be 4 minus y. Then I'm going to have minus, and I need my other equation. But just like in this one, I need this in terms of y. So I need to get x by itself. In order to get x by itself, I need to e both sides. So I'm going to have e to the y equals x. So I'm going to have minus e to the y. Now again, you'll notice there are y's everywhere. There's y values for the bounds. There's y values for the variable. We have a dy at the end. Everything is in terms of y because there's a right and a left instead of a top and a bottom equation here. Now here's the good news. After that, after you set it all up and you write it all out nicely, you type it in the exact same way. You're still going to go to math option 9. And you're not even going to type in y's. Everything that says a y here, you're going to type in as an x. Your calculator doesn't care. It's just an arbitrary variable. It's just that when you're doing this setup on your paper, everything needs to be in terms of y. Even though when you type it in for math option 9, you just type in x's instead of y's. When you do that, your final answer would be 1.792 is the size of that area. All right, the last problem that we're going to do is an actual FRQ question off of the AP test. You are allowed to use a calculator, and in this problem, we're given a picture that has two different areas. We've got the area R, which is this guy right here, and we've got the area S, which is this guy right here. And our job is just to find both areas. Now, we're also given some graphs here. So we're told that this equation right here is tangent of x, and this equation right here is 2 minus x cubed. In order to find these areas, the first thing I'm going to have to do is figure out the intersection point. So I'm going to graph both of these equations on my calculator, and I'm going to find out that these equations intersect at 0.902155505, comma 1.2657507. Now let's work on S first. Now, because I'm asked to find both, and in an FRQ, how I find my answer is really important, I'm going to make sure to very clearly show that I'm finding the area of S first. Now, in this region, so if you kind of ignore R, if you look at just S's region, it looks like the purple is always the top and the blue is always the bottom. We can double check our work there by just sort of drawing one slice. It looks like purple's on the top and blue's on the bottom of that slice, and it's going to be that way no matter which slice we draw in this area. So when we do that, we can figure out that we can do everything in terms of X here. And the reason we can do everything in terms of X is because there's a top and a bottom. Now, the bounds would be the lowest X value, which is 0, to the highest X value, which is 0.902155505, that whole X from our ordered pair. And that's my X values. The top equation here is going to be my purple equation, which we're very thankful is already in terms of X, so it's tangent of X, minus my bottom equation here is going to be my blue I'm sorry, I wrote the wrong one. My purple equation, which is 2 minus x cubed. There we go. And my bottom equation here is going to be tangent of x. Everything here is already in terms of x, so we're kind of good to go. We just need to make sure to put a dx at the end. And my area, S, is going to be 1.160. I'm going to use my calculator, just type that in. Now, the second area that I need to find here is R. And if I look at the area for R, if you kind of zone out on S, it doesn't look like there is a clear top and the bottom. For example, blue is on the top and the x-axis is the bottom for this slice. But for this one over here, purple is the top and the x-axis is the bottom. So sort of the tops switch there. Instead, if we draw our slices horizontally, we can see that the purple is always the right and the blue is always the left. So for area for R, I'm going to do everything in terms of Y. Now that means I'm going to set up my integral using my y values. So the lowest y value here is 0, and the highest y value here is going to be this y value, which is 1.2657507. And instead of doing right top minus bottom, I'm going to do right minus left. Now the right here is my purple equation, but before I can actually put that in to my integral, I need to get x by itself. So I'm going to subtract 2 on both sides. I'm going to divide by a negative. So I'm going to have negative y plus 2 equals x cubed. And then I'm going to cube root both sides. So my purple equation is going to be the cube root of negative y plus 2 minus the blue equation is going to be, I have to get x by itself, so I'm going to use inverse tangent. And I'm going to have inverse tangent of y, dy. Then I'm just going to use my calculator and type this in. Now here's the good news. You don't even have to type in y's. On your calculator, still you type in x's just like you did before. Your calculator just needs a variable there. Doesn't matter if it's x's or y's. When you do that, you get 0.729. All right, that's it for this week's video. Thank you guys so much for watching, and hopefully I will see you soon if you have questions about the practice.